Hi everyone, I'm Vindula Javardhana and I'm presenting our work on learning eco-driving strategies at signalized intersections. This is joint work with my advisor, Kathy Wu at MIT. Greenhouse gas emission has received a significant attention, specifically in the recent years, due to its impact on climate change. Transportation sector in particular contributes to 29% of greenhouse gas emission in US, in which 77% is due to land transportation. We took a closer look at this matter. What we realize is that most of the emission and fuel consumption happen at signalized intersections. This is because traffic signals create stop and go waves, producing excess accelerations and idling events, which in turn increase emission and fuel consumption levels. Therefore, the question is, to what extent can we reduce these emission and fuel consumptions when driving around signalized intersections? Having said that, I believe future cities are going to be operational grounds for fleet of autonomous robots. Self-driving cars or autonomous vehicles is what we usually call them. Therefore, our main question now translates into how we can effectively leverage these autonomous vehicles to reduce emission and fuel consumption levels when approaching and leaving a signalized intersection. This problem is usually referred as eco-driving in the literature. This is the main motivation for our work. So we have three main objectives. We want to reduce fuel and emission levels without having a significant impact on travel time. Eco-driving has been studied in the literature, specifically in the recent years. Most of this work share a similar set of characteristics and can be broadly classified as model-based methods. Model-based methods for eco-driving usually assume a simplified model of the vehicle dynamics and inter-vehicle dynamics and involve simplified objectives to make the problem more tractable. In recent years, reinforcement learning has also been used, but these methods are limited to single agent control. Our work is different from the rest of the works in few different ways. First, we use model-free reinforcement learning, which means we do not assume a model of the dynamics. We accommodate more realistic objectives of reducing fuel consumption while reducing the impact on travel time as well. We solve the resulting optimization problem from a multi-agent point of view, allowing us to gain more benefit than single-agent control. Here's the high-level optimal control problem for eco-driving around intersections. Our main objective is to reduce fuel consumption and travel time for a fleet of N autonomous vehicles that approach and leave a signalized intersection. Since there is a general agreement that low fuel consumption can lead to low emissions, we do not specifically use emission reduction as a separate objective, but rather measure the emission levels from the resultant policy. We intend to control the accelerations of the vehicles under some car following dynamics and predefined requirements on the distance each vehicle needs to travel once they enter the control region and until they leave the control region. We enforce limits on the headway, velocity, and accelerations to ensure passenger comfort, safety, and uninterrupted communications. As I mentioned earlier, solving this eco-driving problem is quite challenging. In our work, we use reinforcement learning to obtain a learning-based solution. The high-level idea of reinforcement learning is quite simple. The agent, in our case an autonomous vehicle, will receive information about the current state of its surroundings and will make a decision on what actions it should perform in the next time step. The environment will be simulated accordingly, and the agent will receive a reward in return, indicating how good the action it took in the previous step. The agent then uses this reward to update its policy. The objective of the update is to maximize the discounted long-term reward. In using reinforcement learning for our eco-driving problem, we formulate the problem as a partially observable Markov decision process and solve it using policy gradient methods. We make few assumptions. First, we assume that vehicle-to-vehicle communication or onboard sensors are available to receive information from nearby vehicles. Second, we also assume infrastructure-to-vehicle communication is also available to obtain signal phase and timing information from the upcoming traffic signal. Now I will walk you through the partially observable MDP that we defined for the eco-driving problem. The observations of the agent include information on its own velocity and position, leading and following vehicle, velocity and position, and the currently active traffic signal phase, and the remaining time to receive the green light in the traffic signal. The control action of the agents are the longitudinal accelerations. Regarding the state transitions, we do not specifically model the state transitions, but rather use advanced microscopic simulations to sample the next state given the current state and the actions of the agents. We recognize that designing a reward function for the eco-driving problem can be quite challenging. This happens because of few reasons. First, our two objective terms are competing with each other. Reducing fuel consumption encourages slower speeds, while reducing travel time encourages higher speeds. Second, rate of change of the reward terms are different in different parts of the composite objective. This makes it hard to define a common weighting scheme for the composite objective. With manual trial and error, we define our reward function by identifying four main cases. With hyperparameter search, we fine-tune it to obtain the best hyperparameter configuration. We use centralized training and decentralized execution with trust region policy optimization algorithm for updating the agent policy. TRPO updates the policy by taking the largest step possible to improve the performance while satisfying a special constraint on how close the new and old policies are allowed to be. The constraint is expressed in terms of scale divergence. Our experimental setup models a single intersection with only through traffic and standard passenger cars. We use VTCPFM fuel consumption model and HBEFA version 3.1 carbon dioxide emission model in our simulations. A fixed time traffic signal control cycle with uniform vehicle arrivals were used. All the simulations were performed in Sumo microscopic traffic simulator. Using the experimental simulations, we try to answer two main research questions. The first question is, how does the proposed control policy compare to naturalistic driving and model-based control methods? Our second question is, how well does the proposed control policy generalize to environments unseen at training time? In answering these questions, we use four baseline controllers to compare the learned behavior. VIDM is the vanilla version of the popular IDM car following model. It models naturalistic human-like driving. NIDM is a noisy version of VIDM that models variability in driving behaviors of humans. MIDM is another variant of VIDM that represents a diverse mix of drivers with varying levels of aggressiveness. ECC is a model-based trajectory optimization method that assumes access to information such as queue discharging rates at the signalized intersection, which is hard to accurately obtain in real world. We first answer the question, how does the proposed control policy compare to naturalistic driving and model-based control baselines? For this case, we look at the learned behavior under 100% autonomous vehicle penetration and compare it with baselines. What you see in this simulation is the behavior we observe with 100% human driver penetration. All vehicles are simulated using VIDM model. It is quite clear to see stop and go waves being formed in front of the intersection, creating vehicle queues. This is not a preferable behavior as it involves unnecessary idling and excess accelerations. In contrast, under 100% autonomous vehicle penetration, we see quite an interesting behavior. Most of the vehicles do not come to a complete stop at the intersection and rather decelerate when approaching the intersection and cruise through the intersection without stopping. This is quite useful behavior to reduce fuel consumption and emission, as now the vehicles avoid idling and perform less excess accelerations than would otherwise require. The benefit of this emergent behavior is quite apparent in the plot on the right. Compared to the human-like driving baselines, the learned behavior achieves significant benefits. Even though the benefit compared to model-based baseline is not as high as the other cases, the reinforcement learning-based approach does not require information such as queue discharge rate at the intersection, which the model-based baseline assumes to have. In summary, we see quite a bit of reduction in emission and fuel consumption, perhaps surprisingly increasing the travel speed as well. Next, we answer our second question. How well does the proposed control policy generalize to environments unseen at training time? For this case, we look at mixed traffic scenarios where human-driven vehicles and autonomous vehicles coexist. Since we train our model with 100% autonomous vehicle penetration, any mixed traffic scenarios naturally fall under out of training distribution. We look at 4 different penetration levels, and for each case, the human drivers are simulated using one of the human-like driving baselines. The 3 plots indicate the improvement in fuel consumption, emission levels, and travel speed when the penetration level changes. What we found to be quite interesting is the nonlinear scaling of the benefits. We see that even 25% of autonomous vehicle penetration can bring at least 50% of the total fuel and emission reduction benefits. This is quite a significant result, as this simply means that we do not necessarily need to wait another decade or more to see an entire fleet of autonomous vehicles to get the benefit of these methods. Even when a smaller fraction of the entire fleet is autonomous vehicles, we can achieve much of the benefits. In conclusion, in this work, we showed reinforcement learning can effectively be used for eco-driving at signalized intersections, and the gains are significant. Also, the generalizability of learned policies to out-of-distribution settings is successful. Future work can span in multiple directions. First, one can consider multiple adjacent intersections in the optimization problem. While this essentially makes the problem harder to solve, the question is to what would be the extra benefit that one can obtain. Second, we also found that the benefit of eco-driving is sensitive to the underlying intersection and the vehicle inflows. In our work, we use most typical intersections and the vehicle inflows, but further studies are encouraged to perform more broader level impact assessments of eco-driving at intersections, potentially as climate change intervention. Thank you.